Okay, so let's introduce or review this idea of second order differential equations. And then spend the rest of today practicing using these things, using the auxiliary equations, which I think I introduced last time. Okay, so what we're going to do is just talk very quickly about what are these differential equations, what are they used for, what process do we go through to solve them, which is the main aim of today, so we can actually start practicing that process, because there's a few steps to go through. So if you just look at the handout I've given you, you'll see, by way of introduction, I've thought of an example. If we think of a mass on a spring, and this is actually not one I've really come up with, it's a just classic example of the use of a differential equation. And we find if we look at these things, consider this model, and we look at the mass here on the spring, then there's three forces acting on this mass. There's the force due to gravity, which is F equals ma. There's a force due to the spring, which is minus kx, where k is a spring constant. And then there's also a drag force acting on this mass as it moves in the liquid. So you could actually think, in any scenario, even if there was nothing here, the mass would be moving through the air, which we can think of as a liquid. So there would be a drag effect to that, which would mean eventually the spring would stop moving. And that drag force is given by here. F force equals minus, because it's a restoring force. This symbol here, eta, is often used to represent the viscosity of the liquid. So this would be the viscosity of the liquid. But also note that the force depends on the velocity, v. And so this means that the force that's acting on this mass increases as the speed increases through the liquid. So you think of air resistance of a car, the force increases with speed. So the force depends on the speed that this mass is moving at. If you think of speed, then that's the rate of change of position, x. So we can replace v with dx by dt, a differential, in other words. If you think of what the force due to gravity, that's mass times the acceleration due to gravity, or the acceleration of the body. So in this case, that's the different derivative of the velocity, or the second derivative of x. So we can replace the mass, the force due to gravity, with m d2x by dt squared. And then finally, we've got also the force due to the spring, which is just spring constant times x. So we can write down the force on the mass at any instant as being the force due to gravity being balanced by this force of the spring and the force due to the drag through the liquid. And then if we replace each of those forces with the equation for them, ma minus kx for the spring constant and minus eta v, we can then think of each of these things in terms of x. M d2x by dt squared equals minus kx minus eta dx dt. And then we can arrive at this, which we looked at last time, and recognize that that's a second order ordinary differential equation. There it is. And that's what we're going to be focusing on today. Certainly the first part of today. It's second order because it's got this second order differential in it. It's homogeneous because it's the right hand side is 0, and that's what we're focusing on today, where the right hand side is 0. And then we can think now that it also includes this term which has got a damping effect in it. So there's our second order differential equation. What we need to do is be able to solve equations like that, which would mean we'd then come up with an expression for how this thing is going to oscillate with time. For this particular example, I worked one out, we've come up with a solution. And we're going to be coming up with a solution like this today. And we notice it gives this, look, this sort of oscillation of the spring. So it starts, it moves, and then very quickly the oscillation dies away to virtually 0. So this is what we call pretty well critical damping. It just oscillates to 0 and then stops, which is what you want if you think about a mass on a spring in the car. You don't want the thing bouncing up and down for half an hour. You want it just to absorb the shock and then come to a rest. So that's the ideal sort of oscillating wave function that you want to represent damped spring system for a suspension of a car. Okay, so our overall aim for the whole of this section on differential equations is to solve non-homogeneous second-order differential equations. These are ones where the right-hand side is not equal to 0. And the general solution to equations of this form comes in two parts. So the general solution is given by the complementary function and the particular integral. And the complementary function turns out to be the solution to the homogeneous form of the equation, which is what we're going to be focusing on today. So what we're going to be doing is working towards solving these non-homogeneous ones. But the first part of that process is to solve the homogeneous form. So let's get that clear in our minds and then move on to look at the next bit, which is finding the particular integral. So the first part is to focus on this, the complementary function. So we need to write down what are the order of steps in solving these homogeneous ordinary differential equations. And these are the steps that we follow. 3 steps to follow. Form the auxiliary quadratic equation, which is straightforward. Solve and choose the correct form for the solution. We're going to talk about that in a second. And given certain boundary conditions, find the values of the constants, because we end up with some constants. We need to work out what they are. So let's have a look. First of all, when we formed our auxiliary equation, we solve it. So we try to solve this thing. We end up with 3 possible solutions, as we'll see. The auxiliary equation we end up with is quadratic, which gives us 2 roots. And so there's 3 different situations that I think we mentioned last time. The first one is real and different roots. So we get 2 different roots, k1 and k2. And in that case, we have that sort of solution. So we choose a solution like that. Y equals a e to the k1. So k1 is the first root, plus b e to the k2x, where k2 is the second root to our second solution to our quadratic equation. And then we have to go a step further and find out, if possible, what the values of a and b are. We might end up with a scenario where we've just got one answer, one value for k, in which case the solution has this form, ax plus b, and then all times e to the kx. Again, we would then need to try and find a and b. And the final example we're going to look at is one where we get complex roots, where the roots are negative, and so we need to introduce the imaginary number j, which you can see here. And in that case, we have a solution of this form, e to the alpha x plus a cos beta x plus b sine beta x. And that's going to give us our oscillation with the cos and the sine involved with it. So that's the one we need, which is the most useful to us often. Yeah. Possibly just one in the exam, because the exam is not that long. So if I were to give you more than one of these, then you'd run out of time in the exam to do it. Yeah, you wouldn't want to run out of time. Okay, so let's look at an example. So you've not got this example on the board, and I've run through the solution. So let's look at these examples ourselves now, okay, and see if we can see what's going on. So let's look at the first example that I had on the board, and so example 1. Oops. So let's make a note of this example and work through the solution. and follow the steps. This could be an example of the mass on a spring that we've been looking at, m d2x by dt squared. So the mass would be 4, whatever units we're measuring the mass in, probably kilograms. The second part of this differential equation is the drag part of the equation, which, so in that one, 12 would represent the viscosity of the liquid. And then finally, we've got this K for the restoring force of the spring, so -8. So that could be one sort of scenario. And we want to try and solve this. So step 1, form the auxiliary equation. All we do is replace the differential with m. So we write 4m squared plus 12m minus 8 equals 0. I actually made an error here, of course. If you think back to that, that's minus 8x, isn't it? Because the restoring force also depends on x. So 4m squared plus 12m minus 8 is the auxiliary equation. If you look at the Helm booklet 19.3, which I gave you, the introduction to this talks about why we can replace d2x squared by dt squared by m squared. So if you're interested in seeing how we get to this first step, you can have a look at it, and it tries to talk about the maths involved with that. Okay? All we need to do as an engineer is recognize what's going on. d2x by dt squared is replaced by m squared, dx by dt by m, and the x disappears in the last term, leaving, hopefully a familiar form, a quadratic equation that just needs solving. So that's step 1 done, we form the auxiliary equation. Step 2, solve. So generally, this is the way we solve them. Hopefully you recognize that as the quadratic formula. In any exam, you'd be given this formula on the formula sheet, the quadratic formula, but you know, we've used it enough times now that you probably remember it. So to find the value of m, we use this formula, where a is the coefficient of m squared, b is the coefficient of m, and c is the number, isn't it? So for this particular example, yep, a equals 4, b equals 12, and c equals -8, yes. Okay? So we just now plug those values into this quadratic formula and solve the quadratic equation. So I would like you to do that now, please. Okay, so we get m equals 0.56 and minus 3.56, which means that k1, the first root, is 0.56, and k2, the second root, is minus 3.56. And so we've got 2 roots, and they're real roots. So going back to our table, it's the first example. So the solutions of the form y equals a e to the k1x plus b e to the k2x. That doesn't matter which way around you do it, which one you call which, yeah. The solution just has the form y equals a e to the k1x plus b e to the k2x. So it doesn't matter which one you call which. So the final solution is y equals a e to the 0.56x plus b e to the minus 3.56x. And if we were looking at how this was describing a mass on a spring, then this, of course, would represent the displacement x. And if we were to look at an autograph plot of that, we would get a model of how this spring behaves. So let's have a look at that. Okay, so if we look at this graph, we can see, well, for this particular case, you get that solution, a combination of two exponential functions. One is an exponential growth, 0.56. One is an exponential decay, negative 3.56. So you can see, depending on the values of A and B, we're going to get a combination of a growth and a decay curve, which is what this looks like. So if this was trying to model a mass on a spring, it looks as though the mass is going to come down and then start to go up again before it reaches its 0 point. And so unlikely to be the sort of solution you're going to get for a real world example, okay, of a mass on a spring. But that's the first type of differential equation solution that you might meet, where we get two real distinct roots. So let's have a look now at the second example. And this one will look like this. So this is example 2. I think that was step 3. That was step 3, yes, thanks Rob. Yeah, that was step 3 to solve the differential equation. So example 2, 4d2 x by dt squared plus 8 dx by dt plus 4 equals 0. Okay, so go through the steps. Form the auxiliary equation and then solve step 2 and then write the form of the solution. And I'll just pause it while you have a go. Okay, so this example, don't forget that should be 4x, which I should have put there. Let's have a look at the solution. So example 2, Daniel made a suggestion that if we look at this one, we could divide both sides, everything rather, by 4. So if I divide everything by 4, we look at this equation, the 4 disappears in the second differential, 8 divided by 4 is 2, 4 divided by 4 is 1, and then we're still left with 0 on the right hand side. So that does make it a little bit easier to use the quadratic formula. So if we do this, put the values of 2 and 1 into the quadratic formula, we get k equal to -1. Now, we talked about this last week. This is an example of a perfect square. If we look at the original one, and if you get it in the form where the coefficient of m squared is 1, and this only works if the coefficient of m squared is 1, if we halve the coefficient of m, half of 2 is 1, and square that, we get the number on its own. So if you remember us talking about that being the perfect square. The perfect square gives us the example where you just get one root. And here you can see how the perfect square root works. Look, if I get this form, then I can rewrite that as m plus 1 all squared equals 0. So then square root both sides, m plus 1 equals 0, and k equals -1. So look for this idea of the perfect square root. That means we have the solution of the form y equals ax plus b e to the minus x. So k is -1 in this case, and that is the solution in this example because k equals -1. Plot this on autograph and you get a function that looks like this. If you look at it, it starts at 1 because that's what one of the constants is. So this is assuming a and b are 1. So it starts at 1 and then the wave dies down to 0 just in one go. And this is so the perfect square gives us the example of a perfectly critically damped oscillation. So this is often what you're after. You're after the solution where you get a perfect square, and this gives you the critically damped solution where it just falls to 0 and then stops. And if you think about a shock absorber, for example, that we discussed, this is the perfect solution. It just absorbs the shock. There's no oscillation involved with it. So that is a sort of wave function you get when you get that particular solution. Okay, we've got one more example to look at. And here it is. See if I can write it correctly this time. So this is example 3, 4 d2x by dt squared plus 12 dx by dt plus 20 x equals 0. Try forming the auxiliary equation. This time you'll make it easier for yourself if you divide through by 4 to make the coefficient of m squared 0, and then solve and try and write the solution by looking at the table. Okay, so this example 3 then looks like this. So if I divide both sides by 4, I get this as my auxiliary equation. Sorry, as my differential equation. And then m squared plus 3m plus 5 equals 0 is the auxiliary equation. So using the quadratic formula, put the numbers in, I end up with minus 3 plus or minus the square root of minus 11 over 2. So if you try to do this in one hit on the calculator, you'll get maths error because it tries to work out the square root of minus 11, which it can't do. So you need to split the calculation into its constituent parts using the calculator here. So at this point, what I do is I rewrite this as, remembering that we can rewrite this square root as the square root of 11 times the square root of minus 1, because that's the same as the square root of minus 11. But the square root of minus 1 is j. So I'll rewrite this as this. Minus 3 plus or minus root 11 j all over 2. Now look at this next step. What I then do is I've got to split this into two parts. I split the fraction into minus 3 over 2 plus or minus the square root of 11 over 2 j. And that then gives me my real part of the solution. So this is the real part, and that's alpha, and this is the imaginary part, and that's beta. So that now gives me alpha and beta that I can put into my solution. So minus 3 over 2 is minus 1.5, so alpha is minus 1.5, and root 11 over 2 is 1.66. So I can finally, in my solution, put in y equals e to the minus 1.5x brackets a cos 1.66x plus b sine 1.66x. And that would be my complex solution. Notice, if we look at it, that now we've got some cosine and sine parts to this solution. So we're expecting an oscillation to occur. And if you look at the plot of this, we see that we get that oscillation. Generally, we ignore anything to the left-hand side. We're not interested in what happens before we start our oscillation, negative values of time, because this is generally time on the x-axis. We're only interested in what happens to the model from that point onwards. And if you look at it, the oscillation dies away, but there's a few oscillations before it dies. Okay? And if we look back at autograph that was plotting this, if I were to change the value of the 1.5 in the solution, close this, change the value of this in here, and call this alpha, which is the real part, okay, then if I change the value of alpha, remember that's part of our solution, changing the value of alpha in this thing, we see that that determines how much oscillation you get before it dies away. So this is slightly damped oscillation, become more and more damped oscillation, until eventually you get to the point where, on the previous example, we have approaching critical damping. Okay, so alpha affects how much it oscillates, and the value at alpha equals 0, look, and there's no decay at all. It's just straightforward oscillation with no decay. So alpha determines how much it oscillates, and changing the value of omega in here would change the frequency of oscillation. Okay. So now what I'd like you to do is turn to, in your Helm booklet, page 40 in that book 3 I gave you. And if you look there, you'll see an exercise that asks you to find the general solutions, that is the complementary functions, for the following equations. They're all homogeneous because the right-hand side is 0, so you've got the whole selection of quadratic equations to solve there and get the solutions in the right form. The answers are underneath, so I'll just give you a period of time now to have a go at some of those.